pathfinding. Okie dokie. So, it's our second part on graphs, second lecture. We had a good look at setting things up in the first lecture, didn't we? Had a look at the adjacency list, which is our reference-based structure for documenting the graph. It's obviously easy to draw in mathematical formats. You're drawing it on a piece of paper. We can draw it digitally, but actually representing it in code, well, there's two main ways to do that with an adjacency list, a reference-based structure like a linked list, or in Python, you could have the Pythonic dictionary, which is a nice blend of the two, but is more on the adjacency list side than it is the matrix side. Matrix is the other school of thought, which is a 2D array. Okay, so those are the two main types of approaches you tend to see in programming languages, but of course Python, we can specialize that with our dictionaries and even store sets and lists and all kinds of ways, but tend to be more node by node, what are the connections from each in the node, rather than just a huge grid, which is the matrix format. Okay, so that was our first thing we established in the first part of the lecture, and then we brought back breadth-first search and depth-first search, didn't we? We started to have a look at how they could be applied. If you remember, we applied breadth-first search in terms of Prim's algorithm for finding the minimum spanning tree. That's an application of breadth-first search. You're going to see breadth-first search again in this part with Dijkstra's algorithm. Okay, it's coming up. And then we also had a look at depth-first search as well, didn't we? Remember, that's a stack-based. Breadth-first search is queue-based. But depth-first search, we apply that to topological sorts. So we saw those two ways as well, didn't we? The minimum spanning tree is our courier. Think of how our courier has to fulfill all the different visits he or she has to make to deliver all the parcels. You know, all these parcels you order on Amazon, the courier has to deliver them all, okay? And that's what they would do. They'd work out the easiest path. How do I cover all the things I need to deliver without having to go back on myself, without having to go here and then back on from there. So find the most efficient path to cover all the stops. That's the minimum spanning tree. And then topological sort was just arranging nodes in an order so that we always point forward rather than back. Okay, so we saw how to set up a graph, how to apply breadth-first search and depth-first search, pathfinding, and also minimum spanning trees, and also topological sort. So we actually did cover quite a lot of stuff in the first part. We did look to establish a path between nodes, if you remember. We did apply breadth-first search in its primitive form, just to establish, is there a path between two nodes in a graph, if you remember. We're in New York, weren't we? Well, I think we're going to return to New York in one of our examples in this pathfinding section. Build out a bigger graph and see if we can find optimal paths. But yes, that's our focus for this session. We are trying to find optimal paths. It's not just working out whether there is a path or establishing multiple paths, it's which one is the cheapest, which one is the most efficient. And that's going to be the focus of our session today. Okay, so that's where we're building. So you know the basics, hopefully. We mentioned graph theory, which goes way back to the 19th century in maths, how we draw out things, how we represent networks. Vertices are our nodes, they have edges, they're connected, okay, and they might be weighted, they might be unweighted, directed, undirected, sparse, dense, cyclic, acyclic, there's a number of terms. This looks pretty dense, doesn't it? We've got quite a lot of connections, interconnectivity. So that's a dense graph, probably more than a sparse graph, fewer connections, only one pathway through things. That's it. So we established the descriptive terms, welcome back, and we built out a graph. Here's our breadth-first search algorithm. And do we remember what structure we used? Let's just drill on this one more time. Breadth-first search can be modeled with what type of structure? Do we remember the difference between the two of them? Does anyone remember?
Breadth-first and depth-first.
Okay, and how do we model them? So breadth-first search, how would you model that? What's a fundamental structure?
Sorry, I thought I was asking what the question was.
The question is, how do we model breadth-first search? What's an arrangement of data that we could use? I'll give you a clue. Look at the language. It's even more. Oh, it's a queue. It's a queue. Breadth-first search is with a queue. Breadth-first search is a queue. Depth-first is a stack. Yes. So We need to internalize this, guys. We need to internalize this. So breadth first, remember, is with a queue. Depth first is a stack. Do we have that? It's not quite as explicit, but it would be a stack. Only need to append and remove from the end of it. Okay, and we did that here, didn't we? Yes. So we established that in terms of this graph. Okay, so we're going to build on this. We're going to build on breadth first search because that's essentially where Dijkstra starts with this famous algorithm, which of course is named after Edgar Dijkstra. You may have heard of Dijkstra. It's quite a well-known mathematician and later computer scientist. He was actually at that first NATO conference, which established the waterfall model. The software engineers would probably know that amongst us. Classic waterfall model, that's where it came from. He was on the panel that helped set it up. Software at the time, was over budget. It was delayed, it was late, it was messy, it didn't fulfill the requirements, didn't meet the standards, over budget, costing loads of money. How do we get around this? Well, we have a structured process. And that's indeed what the guys at the time, Edgar Dijkstra being one of them, they set up this waterfall model. Start with your requirements, then your design, then your building, then your testing, and then your maintenance, in that order. Of course, we've iterated over that. We've gone on things like Agile now. It's quite popular, isn't it? Still got similar stages, just in different arrangements, different orders, okay? You might just iterate over one requirement, establish the first requirement and build it, and have a design for it. Take it to the client. Did they like it? Yes, no. If yes, move on. If no, go back, do another sprint. Let's build on that. And we update the requirements, okay? So it's obviously evolved since then, but Edgar Dijkstra was essential to setting up the waterfall model back in the 1960s, okay? So very, very important figure, and was also known for his algorithm, named after himself, Dijkstra's algorithm, which is what's known as a single source shortest path. There's actually an all pairs shortest path as well. It's another type of algorithm we could explore, which is the Flloyd-Warshall, named after the authors, of course. All pairs, but Dijkstra is a single source. What does that mean? Start with one source, single source, okay? One start node, which here is, okay, in this example, A. What are the shortest paths from A to all of the other nodes? And what do we see here? Curly code braces, key colon value, key colon value. This is what type of structure in Python? Very good, it's a dictionary, yeah, so we returned in a dictionary from A. Obviously A to A is the same node, 0, costs nothing to get from where we are, but A to B, 5, A to C, 7, A to D, 15, okay? We don't know exactly what the pathway was to get there, but we've calculated the shortest distance to there. How do we do that? Well, we look at the edge weights, don't we? Remember, the weightings that we give to the connections between the graph, sum them up, and whichever one is the shortest, that is our shortest path, isn't it? Whichever one is the smallest is our shortest path. So if we're prioritizing minimum values, smallest values, what does that also indicate? Think about our heaps. Max heap, min heap, minimum heap, min heap. Yeah, because we want to heapify up the smaller values. Priority queue, in other words, put the smaller values at the start. So we prioritize them over the larger values, which take longer. We want to make sure the shorter ones come first, okay? Prioritize the shortest values, smallest values, which are the shortest paths, okay? So there we go. That's essentially breakfast search. You're going to see that applied. So remember, check all the children, calculate all the weightings, and repeat that, but have a priority queue so that the shorter paths get established, okay? I'll run that through with you. Don't worry, that will come up very soon. That is essentially in nuts and bolts the Dijkstra's algorithm, okay? So if you know those parts of it, if you know breadth-first search, which I've been drilling on, queue, remember, you make sure you use a queue, first in, first out, and depth-first search, stack, LIFO, if you know the components, and then you know how a priority queue works, just put the two together, you've got Dijkstra's algorithm, okay? Sub-problems. We're going to see this in our final lecture series, which is dynamic programming, coming up next week, finding optimal solutions assumes that you can have optimal sub-problems. So if you work out the sub-problems, you can then put them together to get solve a larger problem. Okay, that's essentially where we're looking at. So yes, Dijkstra is a single source. Flloyd-Warshall is all paths. Maybe I should also mention that the runtime of Dijkstra's algorithm tends to be the vertices squared if you've got a nested loop. So you'd probably see a nested loop at some point for all the vertices from a given point. Run again, see where they all lead, add them up. So it's usually O of V squared, V meaning vertices, not N in this case. N is number of elements in a structure. V is number of vertices in a graph. For all of those bounded, that's sort of the worst case if you have to check all of them. But for all pairs, shortest paths, it's actually V cubed, which scales incredibly fast. But there might be some ways to make some efficiencies. If we look at this in dynamic programming in our next series of lectures, our final series of lectures, you might see that. So we'll come back to that. But now we'll just focus on Dijkstra's, okay? Maybe now would be a good opportunity to visualize it for you. Yeah, there's a couple of maybe one last thing is the negative weights. So Dijkstra isn't set up to work with negative edge weights. We probably haven't seen those yet, but you will eventually come across our graphs that have negative weights. These are all positive, if you notice. You might come across some graphs where they're negative. Okay, if you are working with negative weights, there's another algorithm called Bellman-Ford, so that's another good one to use. But let's just start with Dijkstra's. Okay. This is an illustration. Hope you can see that here. And let's just have a look at this. So start from the source node and look for the end node. What's the shortest path? Well, remember, breadth-first search, we look at the children. We look at all of the children, don't we? So we've got two children, two connections, edges, S to 10, and S to there, which is edge weight of 10, edge weight of 12. So currently, if we only consider the children, remember, it's breadth first, it's not depth first. We don't go from child to child to child. We just look at the children, all of the children, breadth first. Okay, well, so far, the shortest path from S to there is 12, and from S to there is 10. We haven't looked very far, that's fine, but what we'll do is we'll just store that as a label. Okay, so that currently that's the shortest path there. If we were to check other connections, so for example, from here to here, we can look at the existing value and add its edge weight, which is what, 19. Is that less than 12? No, it isn't, is it? So we don't store it. Or we don't, well, if we do, we queue it up behind the smallest value. Remember, priority queue, minimum values first, min heaps, min priority queues. So 12 is shortest. That's the shortest way to get to there currently. All right? And then we iterate this principle. We simply go through all the other nodes and sum the edges. So we started with 12. From 12 to get to there, add 1. That gives us 13. Okay, and then check other paths as well. Go through the other nodes, see where the shortest ones are. So from there to there is 12 plus 3, 15. 12 plus 1 plus 3 is 16, so that's not less than 15, so therefore 15 is less. 12 and 3 rather than 12, 1, 3, okay? And we repeat that for all the others, meaning that we can then return that dictionary, remember? From there to there is 12, from there to there is 10, from there to there is 15, from there to there is 13, there to there is 18, and eventually we'll get to our very last node, which should, hopefully, if we've done it correctly, give us the shortest time allowance, the shortest edge weights to get there, the sum of them. Okay, so that's a very efficient example of it. Maybe if I just take that a little bit slower for you, I've actually got some slides which might also illustrate this further, because I appreciate it's complex. There's a lot going on, so maybe let me just run through the slides. Here, just to illustrate this to you. Let's take this as a graph and let's kind of work it through a bit more slowly. Okay, we're going to apply the same algorithm, Dijkstra's algorithm, okay, with this graph. And there's a little, if you want the color coding again, just to make it a little bit clearer, we've got green here for whether it's visited, unvisited, red if it has been visited, yellow if it's currently where we're at. And then remember those labels? That's going to be the box and the numbers, okay? Distance from node to there. All right, so just show you that's the key. That's the notation we're going to use. So let's start here. And if we want to find the shortest path between A and F, remember Dijkstra's eventually returns everything. If we're looking for the exact pathway, we could construct that, of course. Knowing the edge weights, we can reconstruct the pathway. But for now, let's just work through the shortest paths to all of those elements. Okay, so we start at A. I want all the connections from A, remember, Brett first. How many connections do we have from A? 2, B and C, very good. So we look at those two, don't we, in that order. So A to B is 2, so therefore we should expect to see 2 there. And then A to C is 4, so currently shortest path from A to C. Okay, maybe for the eagle-eyed amongst you, we might spot a shorter path to C. Is there a shorter path to C? Ah, very good, because 2 plus 1 is 3. 3 is less than 4. Ah, very good. Okay, so that is coming up. That's the next step. Let's just show you the first step. There we go. We start at A. We've visited that node. That's now red. And we update its children to have the shortest path label, which is, yes, 2 and 4 to start with. But yes, we then set that to be visited. And if we look at B, we now look at its connections, which are to C, to E, and to D. And here's where your point's going to come in, Roger, because you're right. If we take the shortest label from there, which is 2, plus 1, check what the existing label is. It's 4. Well, 3 is less than 4, so update it. Yeah, there we go. Update the labels if they are smaller. The min priority queue, remember? The minimum values come first. So update those. Very good. There you go. So yes, now the shortest path, the shortest time cost is A to C is 3, which is via B. Very good. 2 plus 1 rather than 4. Okay? And then we just repeat the process. So A to B to D, 4 plus 2, 6. B to E, 2 plus 2, 4. Okay, all with me so far? Good, because then that's B visited. And its edges go blue if you see there. Very good. We move on. We try again. Okay, C. What connections does C have? C to E. Yes, it's 3. So 3 plus 3, 6. Is that less than 4? No. So the shortest path is still A, B, E. 2 plus 2 rather than 3 plus 3, 6. So, okay, that we don't update that. All right, we then move on. From there, yes, it wasn't less, so we say it's visited, move to E. What connections does E have? E goes to D and to F, okay, so 4 plus 3, 7, well, that's not less than 6, is it? Remember, 2, 4, 6, so it's actually quicker to go via there, okay, and likewise, to F, so, okay, where do we get to? We got to 2, 4, 4 plus 2 is 6 for there, so currently the shortest path is 6 to F, but we have to check the other nodes, remember, just to see whether that's the case. So let's go to D now. Okay, 6 plus 2, well, that's 8. That's not less than 6. So we should not update 6 to become 8. And then finally, F doesn't have any connections, so we finish there. Okay, so there we go. That gives us the shortest paths to all of these, all the shortest time costs to these different vertices in our network. So we could return that as a dictionary, couldn't we? A0, B2, C3, D6, E4, and F6. That would be our Python dictionary that we get back. That was essentially this, wasn't it? Like I showed you at the start. Okay? But if we want to actually find the path from A to F, that's a slightly different question, because that then requires us to inspect what is that pathway. Okay, and obviously we can see this as humans, we know this, we can kind of zoom in. Oh, well, it's just all the 2's, right? A to B to E to F, that's the quickest pathway to get there. All right, but we might have to potentially modify the algorithm to reconstruct the plan, or if we've stored them in our queues, our priority queues, we'd have to extract them, wouldn't we, from there. We could probably start with the shortest one stored in the first place, because that's probably going to constitute the actual path, isn't it? Because 0 and 2, well, 2's a low number, so is 3. So at least if we stored these values, we could then go from there, couldn't we? 0 plus 2 is 2, plus 2 is then 4, so that would probably indicate that. and then +2 again to get 6. So it is possible, if you stored them, you can then work backwards, reconstruct them, or go forwards, just checking to see whether your values are not exceeding the total size of the total shortest path to get to F. Okay, so 2 different things going on in terms of single source. Get back all of the paths, get back all of the shortest values to each of the vertices, versus actually reconstruct the path to get there. Okay, so how do we get there? It's via B, it's via E and F. Okay, makes sense intuitively. I see a few people nodding. Okay, so it sounds easy, right? Should be easy to implement, shouldn't it? Well, here is the algorithm. So you just have to then, this is a slightly more wordy version of it, but like I said, you know breadth first search, and you know priority queues. So you probably just have to point those out. And we've also got the reconstruct plan, so that's part of it. It is actually a little bit easier without the reconstruct plan, just to get the dictionary, because that is just breadth first search plus priority queue. Reconstruct plan, you just have to work it out backwards where it is. But yes, that is a form of the pseudocode. Should we just have a look in Python? How could we implement that in Python? Let's see if we can make that a little bit easier for you. You know breadth first search, here we go. Here's a sample graph that we're given. There's that pseudocode I just showed you. So you know about this, you know the breadth first search, models a queue. Okay, we add to the end of the queue, move from the front of the queue. If it's a priority queue, we want to put the smaller values at the front of the queue. So we should be able to extract those, the smallest one at the top. Pop 0, okay. Heap queue, remember we had our heap queue library, min heaps. So we can bring that back as well. Priority queue, we're looking for the smallest distance. Whether it's visited, that's our set of values. Okay, heap pop. And explore the neighbours, that's where it comes in. If a shorter path is found, update the priority queue. That was what we mentioned, didn't we? If a shorter path is found, update the value with the smaller value, with the distance and the neighbour. So we are actually storing which node we're looking at. So that's helpful for reconstructing the plan. Okay, and then return it. So there's the pseudocode again. That's a way to start. That is a Dijkstra's algorithm for you to work with, making use of heap queue. And just to remind you of heap queue, remember we had min heaps, max heaps. With a min heap, what value do we expect to see at the top of the binary tree? With a min heap, the smallest value, the minimum value, exactly. So exactly, if you were using a heap, yeah, you would heapify up the smaller value to get to the top of the heap, wouldn't you? That's essentially what we could model this as, if this was a priority queue. And then the reverse is true for a max heap. The maximum values get heapified up as well to become the top of the binary tree. Okay? So it's those components I mentioned right throughout the module, bringing them together. We're putting them together to create something bigger. Okay? So that's what's going on here. As an example of heaps again, if you wanted to check that. We've actually got a negative value in there. Okay, we might talk about negative values. I think for the moment we'll try and simplify and stick with positive values. Here's a graph, so dictionary, you know this, okay? It's an adjacency list. For each of the vertices in a graph, we store a list of its connections, its edges. We store the vertex and we store the time cost, 10, free, okay? And remember I said about infinity earlier? Rather than zeros, because remember zeros would be smaller, wouldn't they? If we had zeros in this diagram, well, 0 is less than 2, isn't it? So it updates to be a shorter path, but of course 0 was supposed to say there's no path. So we wouldn't want to ideally confuse things, just in case we made a wrong step in our algorithm. Oh, not that, this. We would be best placed to actually start with infinity. So super simple, from math, import infinity, and let's initialize the entire graph to have infinity as its starting initial values, and then we update that with the actual values of the graph, just so we don't go wrong. All right, that's what's going on here. And then we bring in the priority queue, the heap, the min heap, okay, and we again update it. We push on the heap if it's less than, okay, returning that as a dictionary. All right, so here we go. Here it is. Here's our dictionary back. So we get this. Obviously, A to A is 0, A to B is 10, A to C is 3, A to D is 5, A to E is 15. That's our dictionary that we get back. That's our single source shortest paths. We can run it for other things as well. And notice if we pass in B as our single source, well, B to A, infinity, which remember implies there's no connection from B to A. And notice if you have a look at the connections from B, that only goes to C and D. It doesn't go to A. And I guess C and D also don't go to A either. So there's no way to ever get from B to A. That's why it's infinity. Okay? The same principle here. From D to E, there's only one way to go from there. I think that's its only connection. From D to E, there we go. Yeah, D to E is 10, doesn't go anywhere else. Okay, so that's a simple way we could implement Dijkstra's algorithm. Hopefully that's demystified it. It might sound like a lot of work, I appreciate that, but I promise you it is the sum of things you've seen before, because you've seen min heaps, you've seen breadth first search, even if we're a little bit not as confident in breadth first search and depth first search, it's a good way to explore it. Okay, and of course you can then split that dictionary up to get individual distances back, okay, and potentially reconstruct the plan from there. All right, so that's Dijkstra's algorithm. If we want to push it a bit further, there's also another algorithm we could look at, which brings in this heuristic. And again, for the AI students, they might have covered heuristics. It's an interesting area of research. But essentially, it's assuming that humans are not a blank canvas. We bring existing knowledge to the table. For example, intuitively, we would know that, to get from High Wycombe to London, we don't need to go via France. That would be going out of the way to come back, wouldn't it? We kind of know intuitively, if we get back a path that says go to France and then come back from France, hang on a minute, that's going to take ages, isn't it? Instinctively, we know it shouldn't take hours, which it shouldn't do, to get from Wycombe to London. It should be relatively quick, right? We should be talking 30 minutes on the train. If we're driving, maybe 40, 50 minutes from Wycombe, driving into London. It shouldn't take 5 hours unless there's roadworks, for example. So therefore, that helps us remove all the other pathways in a breadth first search, doesn't it? Because remember, breadth first search is going to search all pathways there could be. So this is a way to kind of reduce down the number of total paths we actually need to look at. You don't need to go via France, don't need to go via America, via Brazil, anything like that, because we only want to focus on how paths that are close to our estimates. Essentially, the heuristic is the estimate. We sort of estimate how long should it take, and if a path is kind of close to that, then it sounds like it's a good path to take. All right, so it's bringing in this heuristic. It's bringing in this heuristic, okay, by guiding the search. So it starts with Dijkstra's, it modifies Dijkstra's from a breadth first search only to actually weigh up at every point whether the this is like a cell grid format. It will calculate how far each cell is away from the goal and measure that against the heuristic. For example, if there to there is 10 squares, and if we're going out here and that's getting larger and larger, further away from our target, that's probably saying we're going in the wrong direction. Okay. Likewise, if we go to here, okay, we are away, but if we take a turn there, we're actually getting a bit closer, and we move there, we're getting a bit closer. Moving there, we're getting a bit closer. Moving there, we're getting a bit closer. And again, as we move here, we're slowly getting closer. We must be on the right path in that case, especially as we compare it with all the other relative squares. So again, this kind of bubbles out. If you watch it from the start, look how it sort of spans out. Every step of the way, every square, it's measuring, is this square closer to our target, or is it further away from our target? Comparing against the estimate, we know it should only take, if we were, as the crow flies, if we just could limply jump over the barriers, these are barriers, by the way, these grey squares. If we could jump over, it should only take about 10 squares to get there. All right. So if we're getting further away, like 20, 30, 40 squares, probably not helping, right? Probably going too far. It's like going to France to go back to London. Okay. So this is what we can do. We can build in this heuristic, this knowledge, the estimates, into our algorithms, comparing every step. Okay. So That's a good way you can bring some optimization to your pathfinding. So, before I reveal the full source code, why don't we have a look at this? Let's have a look at a demonstration. So let's go back to these slides and let's see this. Okay, so here's a simplified version of this. So we are the start and the goal is the yellow cross. Okay, we've got some barriers. They're the red ones, the red blocks here. So instinctively, if we had a look at this, we know, if we knew the map, if we looked at the map, we could say, well, hang on a minute, it should only take about 5 or 6 squares to get there, right? If we move here, or move there, that should be easy. Likewise, there. It's a little bit longer, but still, you know, shouldn't take as long. Or here, likewise. So really, estimates of over 10 squares are going in the wrong direction. If we go this way, we're getting further and further away. We'll never get to our targets. So really, every step of the way, I want to compare where we're going with the estimates. All right, so we're going to do that. We can codify this with H for heuristic. That's just our estimate distance. How long should it be? G is the movement cost, so that's like the actual distance. Okay, and then what we're going to do is we're going to sum them. So basically saying that gives us a final value to look at which is greater or which is smaller of that set of values. Okay, and in terms of codifying that, that's going to be the green values here. So this is the heuristic. Literally count the squares. Okay, so how many have we got? 1, 2, 3, 4, 5, 6, 7. There you go, there's 7. And then if we went through the barriers, it would be 1, 2, 3, 4, 5. There you go, there's 5. So if we mapped that out, the heuristic, how long should it take? We could put those against all the squares. And then that's H for heuristic. And then G is going to be the actual cost. How long does it actually take to get between them? We've got horizontal movement and diagonal movement. Okay, so 10 is a horizontal and vertical, and then 14, which I think is the sum of the squares, went diagonally. Pythagoras' theorem, I think, essentially. 10 squared plus 10 squared, A squared plus B squared equals C squared, I think, is essentially what's going on there. Square root of C to give us that to the diagonal. Okay, so then what we do, we add them together. So 14 plus 6 and 10 plus 7. So that should be, let's put those values there if you can see these, hopefully. Remember, the green colour was H for heuristic. Blue colour is the actual cost of moving. And then red colours are the sum. What do we call that? F, I think, if we said G was that, yeah. F is G plus H, essentially. So 20, 17, 15. Oh, okay, so 15s are currently looking better, aren't they? They're lower values, so they should be moving us closer to our targets. So let's explore those. That's going to be our next step from there. Okay, and then repeat the process. So 15 to 27, 15 to 29. Okay, well 27 is lower out of those two, but we've also got 15 here, so maybe we should go 15 there as well, okay? Likewise, 15, 27, 15, 29, and then probably the 17s, and then the others, and we just repeat the process. So we get slowly, as we slowly broaden out, remember, like that illustration, until we eventually find the smallest values that get us closer to this goal, which turns out to be this way. Okay, that's just a way you could do this. Bringing in that heuristic means we don't have to exhaust every single pathway like we did in Dijkstra's. Because if we built this using Dijkstra's, we'd check every single thing, wouldn't we? And update all the labels. But notice there are some we didn't even visit. Okay, so that's just an optimal approach to doing this. So again, sounds easy. Here's the pseudocode if you wanted to do it, and also to reconstruct the plan. So it looks like quite a lot. It does look like quite a lot. But the good news, if you've got Dijkstra's down, you can utilize it. You just bring in those extra values, don't you? Hello, welcome back. So as let's have a look at some of the heuristics, because they could be anything. It could be any form of prior knowledge that you have. Euclidean is literally the literal distance between 2 points on a coordinate plane. Okay, so it's just the squares there to give you the actual distance as the crow flies, okay, across barriers and diagonal distances. That's literally as the crow flies. And then you also have Manhattan, which, remember we said New York earlier? The Manhattan, same in Barcelona too, if you've ever been to Barcelona in Spain. It's got that grid format. It's got the grid layout, hasn't it? Each thing is arranged in a block. Each road is a block. So again, we could know if X is 1 metre, or not metre, it'd be mile, wouldn't it? So 1 mile by 2 miles, we can use that to have a reasonable estimate for how long things should take. Okay, so we've got quite a big graph here. I won't go through all of it, but let's imagine we've got a new graph. Delhi, Mumbai, I think we're in India for this graph, Euclidean graph. Let's build this, and let's bring in a heuristic, a literal distance, which is the absolute distance between 2 positions. Put them together, square root them to get the literal distance. And let's bring in A star, which is a modified form of Dijkstra's. So breadth-first search to a degree, but remember it's got the heuristic value, it's got the movement cost, and then the summation of those 2 things to help guide us. All right, so if we were to direct A star at this, it's actually found the shortest path in 6 steps. So we didn't have to exhaust every single connection because it's managed to use the heuristic to guide it. Okay, and return the path as well, so that's also helpful. Reconstructed the plan to give us that. Okay, and then also, what is next? Let's bring in the heap pop and heap push. That's another way to organise this. We've got the exploration of neighbours. Looking at the current vertex, this is our min heap coming in, priority queue. Okay, is this a modified? Yeah, it's a modified form of Dijkstra's. And update the path if it's better. So let's apply this now to the same graph. All right. Oh, and we get back that actual distance. All right. So 2 different versions of it. One which gives you the pathway, one which gives you the literal distance. So good things to be aware of between those 2 vertices. Just need to print out the name of the vertex at that point. But yes, that's the Euclidean distance, the Euclidean heuristic. Estimate, how long should it take as the crow flies? Then here's the Manhattan technique, or Barcelona if you prefer. This is how things are laid out. In New York, it's 34th Street, 35th Street, 42nd Street. But essentially the principle is, again, we know roughly how long things should take. Because if we know this is 1 by 2, or 4 by 5, or whatever the ratio is, we should be able to calculate how long things should take. It's not as the crow flies, it's abiding to the grid structure of the geography, but we know it should take a certain time. For example, if we know these are all 2, that's 2, 4, 6, 8, 10, and then 2 down, 12, for example. If we get paths that are like 20, 30, 40, we know that's too far away, because if this was 35th Street and that was 40th Street, well, it shouldn't be much more than 2 times that, should it? So that's our estimate that we can bring in. Okay, so 2 different estimates, depends on your context, but it is simply a guiding value to help you. It reduces the entire breadth of options that you have to survey. You're trying to optimise here rather than search everything in a brute force fashion. Indeed, in some graphs there are simply too many options to check, so that heuristic is really important to bring in. It'll save you a lot of time. Okay, so let's have a look at this. Let's bring this in, this Manhattan heuristic. This is just a very brief point on the less than operator. I take it you know by now the double underscores, Dunder methods. Less than, you're just overloading it to look at in this case, names within the objects, compare the objects whether they're less than each other or not, which would then root through and check the actual values. Okay, so we've got a big graph here. This is Manhattan. Got a lot of stations, a lot of places. 37th and 5th, 37th and 6th, you know. So it's all laid out in that format. Big thing here. Let's compare modified Dijkstra's with A star. So we can use both now. Let's compare them. How do they compare? Let's look at Dijkstra's. How long does... Oh, did we forget something? I think we forgot to run something. So let's go back and check that. Let's run the graph. And let's run this. And let's run this. There we go. Okay, so it took 39 steps, modified Dijkstra's, to find what we wanted. Let's now run a star. The heuristic, remember? Ooh, 35, so technically less. It still took a few steps to get there, but it was an optimization. It was a reduction from 39 down to 35. Okay, so I hope that gives you something to consider here. Let me just pause. Does that make any kind of sense, what we're trying to do here? There's a lot going on. I appreciate that. But those are two approaches. You might want to start with Dijkstra's. Remember, that's breadth first search plus priority queue. With A star, you just start with breadth first search, but you then have the heuristic to rule out other things that are not taking you towards your goal. Okay. Let me just finish up with some other select things and then we'll wrap up. So Bellman-Ford was for negative weights. It's a way to work with negative weight cycles. Here we go. We've got some negative weights in here. And of course, negative values would still be less than positive values, wouldn't they? So they would rise to be the top of the priority queue. Okay, so that's something we have to be aware of. There might be particular reasons for having negative weights. It could be indicative of cost. It could be some sort of reduction. It could be some sort of game where we save time, we reduce time. It could be that it takes longer. There's a number of different reasons why we might have negative edge weights, but this Bellman-Ford can handle it. It can handle these. As long as there's no cycles, it would have to manage those separately. There's no negative edge weight cycles, which just go round and round and round. It can handle those and update them accordingly. So here, essentially, 3 minus 1 gives you 2, if you added them literally. And likewise, 2 minus 2 gives you 0. 0 minus 2 gives you minus 2. Okay. So that's just the sum of the edges to get from there to there with negative weights. Dijkstra's is going to struggle with that, the negative weights, but Bellman-Ford is set up to handle it. All right, just let you know, it's also important to detect those negative weight cycles so we don't get stuck in there, or at least it lets us know when we do. These ones are positive in this case, so it's not a problem, but let's just run it for where there are negative weights. Here we go, A, B, and then B to E is minus 3, so that should be minus 1. 4 plus 5, that's 9. Minus 1 is obviously quicker though, isn't it? And likewise, 2, 3 minus 2 is also minus 1. So, yes, let's just run Bellman-Ford, just so we can prove this. We've got single source shortest paths, which minus 1, there's E for that. It will give us that back. Okay, so it's just an alternative approach. We're going to take a look more at what Richard Bellman has to say about principle of optimality in dynamic programming. So we're going to get to that. Don't worry, that's coming. But that's just one of his algorithms. I don't think it, well, actually, technically, I don't think he authored it. I think it was ascribed to him by another author. But important to know when you have negative weights in the mix. Here's just a different view of the same thing, just to return back. Here, not a dictionary, but sort of a tabular form of what the vertices and the distances. So that handles negative weights. Okay, from there, well, there's the network flow. Remember, that's more about capacity than cost, although you could use it as cost. We were talking about minimax, wasn't it? We were talking about minimax, weren't we? So this is exactly where minimax is used to calculate minimum flows and maximum flows. If you want to maximize things, maximize flow whilst minimizing disruption, or vice versa, minimize flow, maximize disruption. If you might not want to maximize disruption, but that's the opposite, is maxi-min. Okay. Similar layout in terms of graphs, but referring to capacity rather than cost, time taken between nodes. Okay, so obvious example is roadworks, where you shut down one path because you have to perform maintenance on it. Real life, of course. How are we going to redirect the flow of traffic? And of course, you have to consider the capacity that other roads have. If it's a single track road, that's obviously going to get filled up with double the volume, isn't it? If you take the volume from one road and put it on another, that's going to fill up quite quickly. So that's something to consider. We'll talk a bit more about this when we get to dynamic programming, but just to let you know, this is also part of your optimal path finding, something worth considering. If we created the graph, rather than weights, here model capacity, edges, there's still connections in a network, but here what's the total capacity they can handle? We can go up till 10, we can't go over 10. Likewise, we go up to 15, can't go over 15, okay? So that might also affect how we redirect the flow of our network, okay? And let's bring in some network X here, just so we can visualize some stuff. Oh, I need to run something higher up, I think. I forgot something. Let's run this, let's run this, let's run this. Oh, no, something was still missing. Did I miss something? Maybe it was down below. Let's run some of this. Oh, that's running. Maybe it was in here. Let's have a look at this. Ah, there we go. Sorry, it must have been reordered. So here is just the visualization of this flow distribution before network roadworks. Okay, so it looks like a graph, doesn't it? So they're not costs, they are just maximum capacities between how we send things in a network, okay? So we'll have a look at modeling this with dynamic programming. We'll bring in some minimax algorithms, maxi-min algorithms. Minimax is not technically dynamic programming, but you could still use tabulation and recursion to do this. It's worth saying. But yes, that's just another form of problem that you encounter with graphs and with networks. So there are ways to do that. There's maximum flow calculations with Edmonds-Karp and Flloyd-Warshall. Okay, we could use that, which again, breakfast search, told you it was important. Our Q is coming back, so we're going to make use of that. That's with the Flloyd-Warshall, which is the Edmonds-Karp, which is a specific implementation of Flloyd-Warshall with breakfast search, whether the others are sorted. Okay. To navigate capacity. So if we were to, we've actually got a way to do that. That's built into the network X, nx.algorithms.flow. It might be worth exploring that actually. There's some inbuilt algorithms for you to think about. If you wanted to model this, if we were computing the maximum flow, we can then run that through. So we calculate the maximum flow between A and E, not the place A and E, but between node A and node E. That is the maximum flow, 15 vehicles an hour. So we have to be aware of that if we're going to put roadworks in. If we want to reduce capacity, we have to be aware of that. Okay, after roadworks. Can we still maintain the same capacity if we take something out on C to D, but how do we get 15 capacity? We've got to reroute people via somewhere else to get that maximum capacity. Okay. And here it is redrawn. All right, so that's going to be 5, 5, and 5, I think, through there. If we're going to knock out between C and D, or likewise A 10 plus 5 together is 15. Okay, so that's a way we can model this. All right, so we can bring that in here. So there we go. There's quite a bit there with graphs with two different types of algorithm. Dijkstra's algorithm and A star, and then we can also extend that further with networks, capacity, minimum flow, maximum flow. There's a number of optimal path algorithms. Okay, there's quite a lot to think about. It's quite a bit of code, but break it down, look at the parts you know. Okay, and indeed with dynamic programming, we'll look at some other things as well, like optimal matrix multiplication. There's a number of other problems as well. Fibonacci is a good one to start with. It's an easy one to start with. Recursion, and we'll explore some other options there. But just on graphs, just to wrap up here, we had a good look at Dijkstra's, okay? So we looked at Dijkstra's famous algorithm, single source, shortest path. As long as you're working with non-negative weights, it's going to return all of the shortest paths to all of the other vertices in the graph. That's fantastic. We can reconstruct the plan between that, between a certain pair of vertices if we need them, the adjacent ones. And we also had a look at heuristics. So making use of our prior knowledge, our human knowledge, to reduce the amount of time that we need to spend checking paths that don't help us. We can optimize for that. We can optimize path finding with those heuristics if we codify them. We did have a quick look at Bellman-Ford. That is useful for negative weights. Assuming there's no negative weight cycles, we can factor that in. Okay, that's helpful. I think that can be further optimized with DP, dynamic programming, so we'll see that. And in fact, Dijkstra's is an alternate approach, by the way. That's a greedy algorithm. It prioritizes the local minimum over the over the global minimum. So that's a greedy algorithm, whereas dynamic programming is technically a different style of programming, as is divide and conquer. Okay, so we've had a look at that. Graph, a quick look at networks. We're going to return to these when we look at minimax and maximin. Modeling capacity rather than time and distance, okay? And then there's a way to do that. We'll explore these algorithms further, I think, when we get to dynamic programming, as well as Flloyd-Warshall as well. That's all pairs shortest paths. If you remember Dijkstra's, that had a time complexity of O of V squared, number of vertices squared. If you're checking all of them, because it's a greedy algorithm, remember, there's no optimization there. Flloyd-Warshall, all pairs. Remember, Dijkstra's was single source. Flloyd-Warshall is all pairs. So from any starting points in your graph, that's O of V cubed. So 3 for loops in there, which is costly as that starts scaling. However, it does give you back all of the pairs, all of the shortest paths for all of the pairs. So that is an approach there. Potentially we can improve upon that. We can make some time savings with dynamic programming. So we'll explore that. Okay, so there you go. There's your second part of graphs. Quite a bit to consider, I think. Quite a lot of algorithms to explore. Now's probably a good time just to recover the basics. Just make sure you know how to set up a graph. Pick an adjacency list or an adjacency matrix. Have a go at setting them up. Maybe you want to have a go at some of these initial exercises down here. Just getting the basics set up. And then there's some really fun applications. So we've seen a few of them, haven't we? The maze finding technique, remember that's a stack, that's just depth first search. How do you navigate between a maze? How do you find the optimal path to get from there to there? And return the path, that's depth first search, okay. Path finding, well, I think I hinted at the tube network. You could model the shortest paths. How do I get a route planner? How do I get from Baker Street through to Tottenham Court Road? Is it via Warren Street? Is it via Oxford Circus? Is it another route that's faster? That could be interesting to model. Okay, there's also social networking, by the way, which is a graph, because it's all degrees of separation. Remember on LinkedIn, you get those numbers, first, second, and third. That tells you how many degrees of separation you are. So if I look at Bob's profile, if I'm Nathan, I look at Bob's profile, and I know Hannah, well, therefore, Bob is 2 degrees of separation. Because I know Hannah, and that's only one more from there. Okay, and likewise, they all span out from there. So you could model, you know, a social media graph with this principle too, to work out degrees of separation. This is interesting. At least I think it's interesting. Shortest paths, Manhattan heuristics. Yes, there's a number, and network flows as well, roadworks and things like that. Very realistic. Roadworks happening all the time. You know, how do we ensure capacity is maintained if we're going to remove one of the roads? How do we redirect the traffic? How do we find the optimal alternate routes to maintain that capacity of traffic? So there's quite a lot of interesting problems to grapple with if you're interested in graphs. Pathfinding gets very interesting. But start with the basics, get the basics running, and then build upon those. Okay? So that's probably a good place to land for now. Any questions at this point? Anybody want to ask anything on graphs? No? Happy? Okay, all right, we'll wrap up there then. I'll leave it there. Cool. We'll leave it.